Okay, let's start.
I'll watch your video.
Okay. And they were the ones complaining, we don't know anything.
So where's he going? Well, it seems like they should get right.
They're big shots. They think they can learn it on their own. Okay.
I think about that every time.
You should give an extra credit clip in this class that they want to know about.
Why are you know what I'm gonna tell them, right? Like we're right here.
What?
Yeah, we have to hide it from them too. We'll wait till they leave.
Hey.
Or you just not be a
Watch the video.
You can just not be a snitch.
I'll turn it off.
Cut it out of the video. Don't be a snitch. Let's all get some extra credit here.
Okay, so last time we looked at integration, and we sort of spoke about what it means in terms of area, but right now we're just looking at how to compute them. And it's basically by reversing the derivative, and we saw the rules, and we started doing some examples. So I just want to finish those examples, and then talk about some other stuff. So we had that example, that example.
You're sort of distracting me from my favorite classes. Appreciate it.
Alright. I'll take care of it.
I heard you were talking about favorite classes.
You back in
Do you have any time for
Those are the examples that I wanted to do. And we did some of these. I think we did this, and did we finish this one?
that? Yeah.
Yeah.
I feel like we finished that one.
Yeah.
So we're here.
Yeah.
I don't know if I need that.
Although we probably rushed through that one at the end. But let's actually just finish these guys up and see. Okay, so quickly, how do you do with this one? So we remember that we can just do this term by term. What rule would apply here? Power rule, which means we're going to have to rewrite it. So a lot of these things just rewriting to make it look like the template that you have. And now you apply the rules. Antiderivative of e to the x. What's the integral of e to the x? C to the x, and there's a plus c here. You add 1 to the power, divide by the new power, to a plus c. So this is the integral of x squared. Huh? X cubed over 3, again by the power rule. When we have numbers here, we don't add a plus c because it's going to be irrelevant anyway, because there's a subtraction that takes place according to the fundamental theorem of calculus. So the notation we use is we write a bar instead, and put 0, 1. I don't think I introduced that last time, but that's what we do. We don't put a plus c. So this guy here is what we call the definite integral. And by the fundamental theorem of calculus, we remember that these guys are computed by finding their antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. And to actually do that, the notation for that is we might write f of x just before doing this from A to B. It's just notation. So don't let that confuse you. So that's how we write it. We wouldn't write a plus c. And so what we do now is try to apply this rule. Take the top number and plug it in. minus, parentheses, take the bottom number, plug it in. So the answer here is a 3. Question. Interpret this number. What's the interpretation? Yep.
Oh, that's the area under the line.
Right. So remember what the definite integral gave us. This was the notation for the exact area under the curve, well, the net area under the curve. So that means if we draw the graph x squared, and we look between 0 and 1, and we wanted to find the area of that region, it would be 1/3 units. 1/3 squared units, whatever units your x's are. So this manipulation actually meant something, and that's something you have to remember. And that was an important thing for the test as well. And that was on the bonus for the previous test. But the idea that you can interpret a definite integral as some sort of area was an important idea. So with that being said, let's get through these two. So you're used to dealing with ones with numbers. So the ones without numbers on these guys, these are called indefinite integrals. You perform the rules and then you put a plus c at the end, because remember when you differentiate, there could have been a constant. And if you have a definite integral with numbers on it, you write this notation, plug in the top number, minus the current bottom. And that number will have some interpretation to it, which on the test I'll ask you about this kind of interpretation, the area under the curve. Although you can get a lot more sophisticated with that as well. H. So now perform the rules. And again, e to the x over 2, you can kind of think of this as a half e to the x, so there's no reason to deal with the 2 in the denominator as some separate entity. It's just a constant multiplier, which we know we don't care about. We've seen this before. The integral of e to the x is just itself, and the constant would just stay. This one we've already actually seen here as well. So now we're plugging in 1 and 3. And for things like this is where your algebra would mess you up at this point. That shouldn't have been too difficult, but you have to be very careful with algebra. You use your parentheses and all that stuff. So this is a half e to the 3. I'm going to plug in the top number everywhere. Minus, third open parentheses, and the bottom number. This is e to the 1 plus 1/3. And so we can simplify that. So that's just 9. It will be minus 1/3. So that's 26 over 3. And we have 1/2 e cubed minus e plus. So just plug in the numbers, but you have to be careful, make sure you use your parentheses because the negative sign is distributed and all that. How do you deal with that? 3 over x. Yeah?
3 align absolute value less.
Right. Again, notice that constant factors don't affect your answer that much. They can just hang around. So the fact that there's a 3, the idea is the rule you should be thinking about is we have a rule for 1 over x is the ln of absolute value of x plus c. Remember the absolute values, it's important. The fact that you have 3 over x, just notice that that's really just 3 times 1 over x. So if you have a constant times a function, you want to do the integral. You just integrate the function and leave the constant, similar to derivatives. So this 3 stays, and the integral of 1 over x is the ln of absolute value of x. Again, in this case, we don't put the plus c because there are numbers on this. So we're interpreting this as some sort of area, so there should be some constant value. So again, we're going to plug in 3 ln of 4 minus, not strictly necessary, but get in the habits of using parentheses, 3 ln of 1. What's ln of 1? Log of 1. 0. And so this is just 3 ln 4. Technically, you don't have to write the absolute values here because 4 is a positive number, but it's not wrong to leave it. It might be wrong if you remove it, so just keep it. So that's basically it. I mean, we're just applying the rules here, but things can get, as you know, a lot more sketchy. And so that's why we need the next section. Which is called substitution. So this is Carmen and Allison are missing the good stuff. This is 5.4. Now, probably the best way to describe integration by substitution, it's not directly applying a rule, even though you're going to get to that point, but theoretically it's a way to reverse the chain rule. And that's something that could be explored in depth, but in Calc 1, that's probably not how you think of it, even though you describe it that way. So in the Calc 1, because if you don't have things like these, the only other integrals will be ones where you need to use substitution. So you pretty much use this when a basic rule does not apply. So you should always try to simplify first, because the rule might apply if you simplify. And you want to transform the integral so that a basic rule does apply. So there are a couple types of integrals you will have to compute on the test. There are ones where the rules just directly apply. It's just right there. Oh, that's x to a number. Add 1 to the power divided by the new part. You just apply a rule right away. Not always is it going to be so easy. There are going to be times when you have a complicated function and you can't really apply any rule directly. So for example, if you see something like this, you will notice that as written, the rules cannot deal with that integral. But it turns out it's a doable integral. And I'm going to do that after I describe the method of substitution. Right. So again, remember your algebra. Don't do things like, oh, just take the square root of this and square root of that and multiply out. You cannot distribute a square root across a sum. Right? So you can't simplify that to use the power rule. It's not going to work. You can't really simplify. So the question is, how do you deal with something like that? When you see an integral like this, you use the method of substitution, and in Calc 1, that's easy because this is literally the only method besides the basic rules that you will ever need to know in a Calc 1 class. You're never going to go beyond that. So if the basic rule doesn't work, you know you have to use substitution. So once you know that, this is how the method works. One. U is typically the variable that we use, and a lot of students for that reason call it U substitution, but you don't have to substitute U, it's the standard thing to substitute. And I'll show you what I mean. So you're going to replace an expression in the integral with U. U must fulfill two criteria, right? So you don't just randomly replace whatever, right? You need to make sure that the thing you replace fulfills two properties, right? One, it will make the integral simpler. By simpler, I mean it will make the integral start to look like something that a basic rule can work on, whereas it didn't before. So usually your U is going to be the guy, you're going to read through the integral, and you're going to kind of find that guy that makes it complicated. So for example, in this example, what really makes this complicated is the thing under the square root, right? Because there's a sum under the square root. If it wasn't a plus sign, I could just rewrite that using algebra and use the power root. It wouldn't be a problem. What makes this complicated is there's a sum under a radical, and that I don't know how to deal with. So there's going to be some sort of complication. The idea is get rid of that by making it a single variable, right? So that's one thing. So by simpler, I mean make it look more like something a basic rule can handle. But it's important. The second thing is also important. There are times when you might have several options for things to substitute. There might be a couple places in the function that looks complicated, but you need to make sure that the second criteria is fulfilled, and that is the derivative of what you substitute must be a factor elsewhere in the integral. So we're transforming this integral, and you're going to have to be changing everything, including the dx part of the integral. And for that to work, you sort of need the derivative to work out. One thing here, if off by a constant factor, it's okay. Right? You can just factor. Constants are easy to deal with. We can always factor them off. They're not going to be. So the variable part of the function, you want to be able to see elsewhere in the function. So let me do an example. Let me continue. This is just step one. Step two is now you're going to substitute once you find U, differentiate to find dE, substitute these in your integral. The integral will now be simpler in the sense that a basic rule would now apply. Perform the integration. It's called back substitution because your answer will have u's in it, and the original question might have had x or some other variable. And so once you get an answer in u's, you have to replace the u's with the original function of x, and that's called back substitute. It might be a little confusing just reading the description, but kind of understand the description, and an example would make it clearer. But again, substitution, it is going to be something that takes some practice to really start to get used to and really start to be able to see what you want to substitute, what you want to substitute, things like that. So, let's try this basic example here. So faced with a random integral, the first thing you're going to look for is, can I simplify that to use a basic rule? In this case, you can't. So now we're in the situation where, because we're in Calc 1, we know, okay, if I can't simplify it, it has to be a U substitution. In a higher calculus class, that would not be the case, but in Calc 1, that's literally always the case. If a basic rule doesn't work, it's substitution. Okay. So we know we're going to have to substitute something. So the goal is, we're going to replace an expression with U in the integral. It must have fit two goals. One, it's going to make the integral simpler, and two, its derivative must be somewhere else in the function. So one, you would ask yourself, what is making this complicated? The x squared plus 1 makes it complicated. Let me see if substituting x squared plus 1 will actually work. So you will try that. So now you have to actually differentiate. So to do that, you're going to find the derivative of u with respect to x. You're going to get 2x. Now, you check step 2. Is the derivative somewhere else in the function? Even if it's on that constant factor, it will be okay. So you can essentially sort of for a second ignore the 2. Is the x somewhere else in the function? Yes, the x is right there. That means you had a good substitution. It'll make things simpler, and when I took its derivative, it's there somewhere else in the function. So that means your du is equal to 2x dx. By the way, this line here is usually skipped, and they usually jump straight from here to here. So you usually don't write this out, even though technically that's what's happening. And there are a couple ways to proceed here, but usually what students like to do is they like to solve for the dx. That seems to be the simplest thing, so they can literally just swap it out. So that's sort of how I teach it. So if I solve for the dx, I would be dividing both sides by 2x, and then get du over 2x. So I'm faced with an integral. The basic rules don't work. So I want to do a substitution. I pick something that, if it's substituted for a single variable, will make this guy easier, and its derivative is somewhere else in the function. By doing that, I can solve for the dx. And now what I'm going to do is I'm literally going to substitute everything in. Plug in u for this guy, and plug in dx, I'm going to replace with this guy. So that's why it's called substitution. We're swapping things out. We're substituting the x expressions for the u expressions. And you're going to see something magical happen. So now I start to swap things out. The x I didn't change, so I'm going to leave that. But what's under the square root is now u, right? Because my u is the x squared plus 1. So my x squared plus 1, I'm going to replace with u. This part here is u. Also, the dx part, this part here, is now du over 2x. And so instead of writing dx, I'm going to write du over 2x. Now what you'll notice is going to happen, the x's are going to cancel. Which should happen, you should have no x's. Once you did a proper substitution, there should be none of the old variables should be left over. There's also a 2 here in the denominator, but that's a function, it's okay, I can factor that out. And then the integral is transformed into that guy. That guy is simpler, we can actually deal with that. Because that's just something the power root can work with. So I rewrite this as u to the half, and perform the power rule. Add 1 to the power, divide by the u. So this is 1/3 u to the 3/5. Now one thing you realize is that this is the answer, this is the integral. The problem is, there's a u in my answer. The original question has x as the variable. So this is what step 4 is talking about, back substituting. I'm simply going to replace the u with the original expression that I substituted. So that is going to be 1/3 x squared plus 1, 3 over 2 plus c. And that is it. And that is something you can check. You can check and see if you differentiate this, you will get that. So a lot happened there. You'll have to get used to it. So let's do a couple more examples. I'm going to make a slight variation to this one. We'll run through that quickly, but I just want you to see some of the possible options. So let's say you see something like that. In principle, it's exactly the same as the last one. Just make it look a little uglier. And now we have several viable options. So you look at something like that, you realize I can't simplify that to apply a basic rule. So the power rule does not apply here. But now we have a couple of things that seem complicated. We have the 4x squared and we have the x cubed plus 3. So u equals the 4x squared might be an option, versus u equals the x cubed plus 3. Now what do you think is the better option to substitute? Yeah?
X cubed, because the derivative is x squared.
Right.
X squared in it.
This guy would be the better substitution for 2 reasons. 1, that will make the thing simpler. Dealing with the x squared is not really going to simplify things too much because I'm still going to have a sum under the radical. So on count 1, this is actually a lot better. 2, if I differentiate this guy, I will have 8x, whereas this one, if I differentiate, I will have the 3x squared. Now, what's left over in the integral, if I replace this with u, the thing that's left over is an x squared, which means the x is not enough to replace the other guy, right? So when I take the derivative, that is not somewhere else in the function. there's more there, right? So this would be a bad substitution, whereas this would be a good substitution, because here we have that x squared and we have the x squared, right? So there might be cases where there might be several things that are enticing to you to substitute, but you have to remember the two rules. You want to make them simpler, and you have to make sure the derivative is somewhere else in the function, and there should be nothing left over. There should be no x's or anything left over after you do the substitution. Now, and again, don't worry about the fact that this is a 3x squared and that's a 4x squared. Constants are fine, you can factor them out. So don't worry about that. But the function part of your derivative must be elsewhere in the function for the thing to work out. So if you're faced with a couple options, you need to make sure that what you choose to replace the u with, its derivative needs to be something else. And it needs to be a factor. It has to be this times that. It's multiplied. So. Let's quickly run through this one so you can see it. So I see something like that. This makes it complicated, and I can't simplify to get rid of it, so I'm going to say u equals x cubed plus 3. I immediately find my derivative. I check that x squared, good substitution. So now I solve for my dx. And so now I decide to plug everything in. Let me do it over here. Go back to the original integral. The 4x squared, I didn't do anything with that, so I leave it alone. Under the radical, I have x cubed plus 3. I replace that with u. My dx is replaced with du over 3x squared. X squares here cancel, so all my x are gone. That's good. If there are any x's left over, it means something went wrong. The 4 is a constant, the 3 is a constant. They make things look kind of ugly. Let me just factor them out. And that's what we were left with. We did something like this before. Rewrite as u to the half so we can apply the power rule. Add 1 to the power, divide by the new power. Now we can just 8, 9, u to the 3 over 2, which now I would simply rewrite in terms of x's. 8 over 9, my u is x cubed plus 1 to the 3 over 2. Again, you can check differentiating that. Gives me here. That one, what would you substitute? Yeah?
X squared plus 1. What's
It's a trick question, it's not a substitution question. But if you thought it was a substitution question and you went along and did this, what would have been the issue?
You can't cancel plus 1.
If you do the du, you get the 2x. But there's a plus 1. That's a problem, right? You don't have 2x multiplying the thing. You have the 2x plus 1 multiplying the thing. So the fact that there's a plus 1 there actually will mess things up. The derivative is not elsewhere in the function. right? Because that plus 1 messes things up. So the right way to you just expand the parentheses and do the power rule. So don't get too substitution happy. Now that you've learned substitution, you feel all cool. That's okay, but don't use it when you don't need to. So that was a trick question. What about this one? That looks mighty complicated. Yeah.
You want to solve that, right?
Yeah. Well,
U equals U equals 1 over x.
equals 1 over x.
And then du would be 1 over x squared, or du over.
D would be minus 1 over x squared dx. And there's you have 1 over x squared, which is probably something I should mention here. Notice that you see an x squared here, but saying something like u equals x squared would be a bad idea because it's not actually x squared, it's 1 over x squared. The x squared is in the denominator, and that matters. So that shouldn't even be an option in case you were thinking about it. One thing you'd realize is that having a rational function in the power of e, that's incredibly complicated. So if you have e to some weird power, that's probably where you should be focused on. And then finding the derivative of that, you will realize that this guy shows up. So be careful of mixing up a function and 1 over a function. If a function is in the denominator, don't think of it as x squared. It's 1 over x squared. Now, that being said, we have 1 over x squared from our derivative, which means I can solve for dx now. Now my dx is just going to be minus x squared du. And so now I can substitute that in. This is e to the u over x squared times my dx is minus x squared du. And the x squared in the top will cancel the x squared in the bottom. That negative sign I can factor out. And oh look, it's a very simple integral. I have a rule for that. The antiderivative of e to the u is just e to the u. And so now I just replace the u with what it is. It's 1 over x. And that's it. First thing you check, can I simplify that to use the power rule? The answer is no, because there's a sum in the denominator. You can't distribute a fraction across a sum in the denominator. So, options. Maybe u equals 4x squared. Good option. Alright, the derivative wouldn't work. Okay, so one, the denominator is making it complicated because there's a sum in the denominator. If it was just a single term in the denominator, I could just use algebra and simplify it, but the sum makes it complicated. Equals 3 plus x cubed. So what I would do, du would be 3x squared dx. So now I want to make sure that there's an x squared dx somewhere else in the function. So there's an x squared dx. There's an x squared dx. Constant doesn't matter, I can factor them off. So what I would do here is solve for dx. And now I'm going to plug everything in. This is 4x squared over the denominator I replaced with u. my dx gets replaced with du over 3x squared. The x squares cancel. 4 over 3, constant, factor that out. How do I do with that?
1 over u, or negative 1 over u squared.
No.
Negative 1 over u
You're doing the opposite of what you should.
squared. Oh,
We're integrating.
that's ln impossible.
I know I've been differentiating this whole semester and now I want you to literally go in reverse. It can get confusing sometimes, but remember that sign means you want to do the opposite. That actually becomes an ln. And now I replace that with, and in this case the absolute values are important because that can become negative on the inside, so that would be an issue. Practice this. The area between curves question is of course optional, so you don't technically have to worry about that. But it's not a difficult idea if you really want to do it. Basically, it's you take the antiderivative of the top curve minus the bottom curve is essentially the issue with area. Find the area on the top minus the area on the bottom, you get the area in between, and the limits would usually come from the intersection. But with this, you should have enough for the test. And I'll see you guys tomorrow.
Do you have any walk-me hours?
Huh?
Do you have any walk-me hours?
Walk me.
Office hours. Half hours.